How challenging is calibrating qubits when building a quantum computer? Imagine trying to tune dozens of tiny, delicate instruments all at once, each one constantly changing and interacting with its neighbors. That's what calibrating qubits feels like in a quantum computer. Every qubit needs precise adjustments to work correctly, and these adjustments are not a one-time thing. They have to be repeated often because environmental factors like temperature, electromagnetic interference, and hardware aging cause the parameters to drift. Each qubit has dozens of control settings, like frequency detuning, pulse shapes, timing, and amplitude. These settings must be fine-tuned to ensure the qubit performs quantum operations, called gates, with high accuracy. Small errors in these gates can quickly add up and ruin the entire calculation. That's why calibration is so vital and so difficult. Crosstalk adds another layer of complexity. When you control one qubit, it can unintentionally influence neighboring qubits because they are physically close and electronically connected. Adjusting one qubit's parameters might cause errors in others, so calibration becomes a balancing act. Often, calibration has to be done sequentially, one qubit at a time, which takes a lot of time and effort. As the number of qubits increases from a handful to hundreds or thousands, the calibration process becomes exponentially more complicated. Manually tuning each qubit is no longer practical. It can take weeks or even months to calibrate a large system. This creates a bottleneck that slows down the development of bigger quantum computers. The hardware used to control qubits also plays a role. The physical wiring, microwave lines, lasers, and control electronics must be carefully managed. As the system grows, maintaining stable and accurate control signals becomes more challenging. Any small fluctuation can cause errors, so constant fine-tuning is necessary. Environmental noise and hardware imperfections make calibration even harder. Quantum states are fragile, and any disturbance can cause decoherence, which is the loss of quantum information. Calibration aims to minimize these errors, but it's a continuous process because conditions are always changing. To overcome these hurdles, researchers are turning to automation and artificial intelligence. Machine learning algorithms can quickly optimize control parameters, reducing the time and effort needed for calibration. These tools can handle complex interactions and adapt to changes in real time, making large-scale calibration more feasible. In summary, calibrating qubits is a highly demanding task. It involves managing hundreds of parameters, dealing with crosstalk, environmental noise, and scaling issues. While it remains a major challenge, advances in automation and AI are helping to make the process faster and more reliable. Overcoming calibration hurdles is essential for building larger, more dependable quantum computers in the future.